Hey there, and welcome. So, we've talked about how a single lonely charge creates an electric field around it. But let's be real, the universe is rarely that simple. Today, we're going to tackle what happens when charges team up, when you have a whole system of them all interacting at once. Let's get into it.
So this is really the big question, right? We've got the basics down for one charge, but what happens when you have two or three or, a gazillion charges all pushing and pulling on a single point in space? How on earth do we figure out their combined effect?
The thing is, in the real world, we're almost always dealing with systems of many charges. I mean, think about it. From the very atoms that make you to the complex electronics inside your phone, it's all about countless charges interacting. So understanding their combined effect isn't just a neat trick, it's absolutely fundamental. Okay, take a look at this. This image really visualizes the problem we're facing. You see that point P? That's our spot of interest. And then you've got all these different charges, Q1, Q2, Q3, and each one is creating its very own electric field right there at point P. Notice how each field, E1, E2, and so on, is an arrow. It's a vector, and they're all pointing in their own crazy directions. It looks like a total mess, but believe it or not, physics has a beautifully simple rule to sort this all out. And here it is. That's the secret sauce. To find the total, the net electric field, you don't need some crazy, complicated formula. You just add up all the individual field vectors. Seriously, it's kind of like a big game of tug-of-war. If you have a bunch of people all pulling on a rope from different angles, the final way the rope moves is just the sum of all their individual pulls. Now, this powerful yet incredibly simple idea has an official name, this superposition principle. You should really think of this as the master key that lets us unlock the electric field for any arrangement of charges, no matter how complicated it seems. And here's the formal definition. Pay close attention to that last part, as if each were acting alone. This is the truly mind-blowing part. It means that the charges don't interfere with each other's fields. You can calculate the field from charge 1, and then you can pretend it doesn't exist while you calculate the field from charge 2, and so on for all of them. Then, at the very end, you just add it all up. It's so elegant. And of course, this is how we write it down in the language of math. Now, I know, it looks a little intimidating, but let's break it down. It's actually pretty simple. E of R, that's the total field we're looking for. This first bit is just our friendly old constant. Now, this big Greek letter sigma, that's just a command. It means add up everything that comes next. And what are we adding up? Well, for each individual charge, which we label I, we take its charge value, Qi, divide by its distance squared from our point, and then, this is important, multiply by this little r hat. That r hat is a unit vector. Think of it as just a little arrow whose only job is to point us in the right direction for that one field. So really, the whole formula is just a precise recipe for what we just said. Find each field vector, then add them all. All right. Theory is one thing, but to really get a feel for the superposition principle, you gotta see it in action. So let's get our hands dirty and work through an example with some actual numbers. Okay, so here's our playground. We've got a positive charge Q1 and a negative charge Q2. They have the same strength, just opposite signs. They're sitting 0.1 meters apart. Our mission, should we choose to accept it, is to find the total electric field at 3 different spots. Point A, smack dab in the middle, point B, off to the left, and point C, floating right above the middle. Let's start with the easy one. Point A, right in the center. Now think about this. The field from the positive charge, Q1, points away from it, so that's to the right. And the field from the negative charge, Q2, points towards it, which is also to the right. How cool is that? Since both vectors are pointing in the exact same direction, adding them is super easy. We just add their magnitudes. And when you plug in the numbers for the charges and the distances and you do that addition, you get a total electric field at point A of 7.2 times 10 to the 4 newtons per coulomb. And it's pointing squarely to the right. That's the combined muscle of both charges working together at that spot. Now, what about the other points? This is where it gets really interesting. At point B, the fields are in that tug-of-war I mentioned. The positive charge is closer, so its field pointing left is stronger. The negative charge is farther, so its field pointing right is weaker. They fight each other, so we end up subtracting their strengths. And then there's point C. Here, each charge creates a field pointing at an angle. To add them up, you have to use a little trigonometry. But what's really neat is that the up part of one field perfectly cancels out the down part of the other. All you're left with are the two rightward parts, which team up. It's a perfect example of why the direction of these vectors is everything. So, okay, we've seen how to do the math, but this all begs a much deeper question. Why did physicists even bother inventing this whole concept of a field? Why not just talk about forces between charges? Well, the answer tells us something truly profound about how the universe works. This quote right here is the key to everything. The electric field isn't just a convenient math trick, you see. It's a real physical thing. It's the stuff that fills the empty space between charges and actually carries the force from one to another. It has energy, it has momentum, and, crucially, it doesn't work instantly. And this is the clincher. If you take a charge right here and you wiggle it, another charge a light year away does not feel that wiggle instantly. It can't. A ripple, a disturbance in the electric field has to travel outwards from your wiggle. And the speed of that ripple? It's the ultimate speed limit of the universe, the speed of light, c. The field is what explains this cosmic time delay. Woo, we have covered a lot of ground, from the basic idea to a hands-on example, all the way to its deep physical meaning. So let's bring it all home and summarize the key formulas and the big ideas you should take away from all this. Here you go. This is your essential toolkit. First up, you have the basic formula for the field from a single point charge. Next, the superposition principle, stated as simply as possible. Just add up the vectors. And finally, the general form, which elegantly combines those first two ideas into one super powerful equation that works for any system of charges. So, if you're going to remember just a few things, make it these. 1. Fields add as vectors. Direction, direction, direction is critical. 2. The superposition principle is your best friend for solving complex problems. Just break it down. And maybe most importantly, the electric field isn't just a bunch of math. It's a real, fundamental part of the very fabric of our universe. And I'll leave you with one last question to chew on. We said that a disturbance, a ripple, in the electric field travels at speed c, and we all know c as the speed of light. So, what does that imply? If wiggling a charge creates a ripple in the field that travels at the speed of light, could that ripple be light? That question right there is the doorway to the entire theory of electromagnetic waves. Thanks so much for joining me.